So we're going to talk about a few more approximation methods that are a little bit better than the Euler method. We're going to go back to our example, y prime equals y, and with initial value y of 0 equals 1. And we already know now for sure, because we solved it with separation of variables, the answer to this problem, initial value problem, is going to be y equals e to the x. And we're still going to keep our delta x equals 1. We talked about how if we made that smaller, certainly really small, like 0.001, Euler's method would actually be pretty good. Should be Euler's method. But actually, the other way, instead of making delta x really small and then making it really hard to do by hand, you have to do it on a computer, we can make some improvements to the method. So let's see what we were doing. So y0 equals 1 for sure. So we know that y prime of 0 equals 1. And before, what we were doing is we were starting at this point 0, 1, and we were using that slope to get to our next point, our y value at 1. And what we were getting was y of 1 was approximately 2. We were going with a slope of 1, and then our y prime of 1 was approximately 2. Now we know that our actual answer, that's right, actual, y of 1 is going to be e to the 1 is e, which is about 2.7. So that's way off already. And then as we keep going, if we just assume this is the real value, our error compounds. So that's no good. So let's try to make it a little bit better before we keep going. Now if we look here, we're approximating the slope here by 1, and we're approximating the slope here by 2. And those are both not accurate. This one's too small for this interval, and this one's too big for this interval. So what if we just took the average? I'm going to call it m1 for a slope of the first interval. Is going to be, so what are our two possible slopes? Well, the one I was taking before was 1, and the one at the end of the interval is 2. So I'm going to do 1 plus 2 over 2 is 3/2 or 1.5. Now, without having drawn anything, I'm going to go back to my point 0, 1, and I'm going to calculate y1 again. So I start with a value of 1 plus, and now I'm going to take this slope of 1.5, and my change in x is 1, so I'm walking along that slope for a delta x of 1. That's going to give me 2.5. Graphically, what does that mean? I start at this value of 1. I go with a slope of 1.5 for a length of 1. I end up at 2.5. And let's check that, well, the actual value is 2.7. So this is way closer than my original Euler method. They gave us a value of 2. Okay, then we keep going. So every time we got to do this work twice. It's a little more work, but for a lot more accuracy. Okay, so y prime is still y, so y prime is about 2.5, and then we do our original Euler method first, y of 2. We start at 2.5, we go another slope of 2.5 would be about 5, and then y prime of 2 is about 5, and then we're going to take the average of the slope at the beginning of the interval of 2.5, slope at the end of the interval of 5. They're both not accurate, but the average is going to be a little bit closer. So 2.5 plus 5 over 2 is 3.75. So then our actual estimate, better estimate of y of 2 instead of 5 is going to be, and we start with our y of 1, which we took to be 2.5, plus our slope along an interval of size 1 is going to be 6.25. Let's see, 3, 4, 5, 6, 6.25. So that's what that looked like. And then our actual value is e squared, which is about 7.39. And our original Euler, by the way, was 4, I believe. Okay, so in our original Euler, we were almost off by a factor of 2 already. Here we're still, it's not great, but we're 1 away. So even though the error is compounding, it's not that bad. And if we kept going, I'm not going to show you all this work, but remember our original Euler, we got y of 4 was about 16, and then the actual answer was e to the 4th, which was about 54.6. This was off by a factor of 4. That was terrible. It's not a good approximation at all. In our improved Euler method, if we kept going, we would get y of 4 is about 39.0625. That's still not good. We're off by less than 50%. So certainly better than off by over 300%. So still not good, but way better than the original Euler method.